Welcome to G Fun Facts Online. Today, we are diving straight into one of the most ambitious and critical engineering challenges of the 21st century, the transition to a global green hydrogen economy. We hear a lot about green hydrogen holding the key to decarbonizing our heavy industries, maritime shipping, and aviation. It is produced by splitting water using electricity from renewable sources like wind and solar. But as the world races to scale up production to multi-gigawatt levels, the industry faces two silent, deeply hidden, but monumental bottlenecks within the architecture of modern electrolyzers. Specifically, we are talking about the reliance on toxic per- and polyfluoroalkyl substances, known as PFAS, and the severe, geological scarcity of a metal called iridium. For decades, proton exchange membrane, or PEEM water electrolysis, has been the absolute gold standard for green hydrogen production. It has a high efficiency, a compact footprint, and an amazing ability to handle the wildly fluctuating power loads of renewable energy grids. When the wind blows hard or the sun shines bright, a PEM electrolyzer can ramp up instantly to capture that energy. However, traditional PEM electrolyzers depend heavily on two deeply problematic materials. The first is Nafion, a PFAS-based polymer membrane. The second is iridium, an ultra-rare platinum group metal required to catalyze the oxygen evolution reaction. With global regulatory bodies like the European Union moving rapidly to restrict these forever chemicals, and the global supply of iridium strictly capped by natural geological limits, the hydrogen industry is being forced to innovate rapidly or face complete stagnation. The race is now on to engineer the absolute next generation of electrolyzers. From revolutionary silicon oxide membranes to ultra-low iridium nanotechnology, and entirely iridium-free anion exchange membrane architectures, the landscape of water electrolysis is undergoing a radical and rapid transformation. Let us start by unpacking the PFAS predicament and the monumental task of moving beyond forever chemicals. Since its development by DuPont in the late 1960s, Nafion has completely dominated the electrochemical landscape. As a perfluorosulfonic acid polymer, it boasts a truly unique combination of chemical stability, high proton conductivity, and mechanical durability. In simple terms, it is uniquely capable of surviving the highly corrosive, extremely acidic environment of a electrolyzer, while still allowing protons to pass through efficiently. But there is a massive catch. Nafion is a PFAS. These synthetic compounds are characterized by strong carbon-to-fluorine bonds, which are among the strongest bonds in organic chemistry. This makes them incredibly resistant to degradation. When these materials are disposed of or slowly degrade, they leach into the environment. They persist indefinitely, they accumulate in the food chain, and they pose severe risks to ecological and human health. Driven by these environmental and health concerns, the European Union and other global regulatory bodies are spearheading aggressive initiatives to heavily restrict or outright ban the use of PFAS. This impending legislative cliff has catalyzed an industry-wide pivot toward fluorine-free proton exchange membranes. But the challenge here is absolutely monumental. Researchers have to match or exceed the performance of a material that has enjoyed a 50-year head start in research and development. Fortunately, several commercial and academic entities are making massive strides in polymer chemistry. For example, researchers at the Industrial Technology Research Institute have developed advanced hydrocarbon-based membranes utilizing sulfonated polyether ether ketone, or SPEEK, by precisely controlling the sulfonation degree to between 50 and 65% and utilizing a unique cross-linking strategy with multifunctional agents. These membranes form incredibly strong covalent networks. This drastically reduces membrane swelling while maintaining the critical ion channels needed for proton transport. Similarly, industrial giants like Arkema have introduced PVDF-based alternatives. Their technology incorporates sulfonated side chains to achieve high proton conductivity while maintaining excellent mechanical stability through advanced surface modification techniques that enhance hydrophilicity, meaning they attract water more effectively. These fluorine-free or reduced fluorine membranes are achieving conductivity values of 0.08 to 0.12 Siemens per centimeter under standard operating conditions. This presents a highly viable drop in replacement for traditional materials. But we are not just looking at polymers. At the absolute cutting edge of materials science, researchers are exploring the use of functionalized graphene oxide to create completely novel electrolytic pathways. Recent laboratory studies have investigated sulfonated graphene oxide and graphene oxide naphthalene sulfonate as PFAS-free alternatives. Graphene is essentially a single layer of carbon atoms, and when functionalized this way, it significantly outperforms naphthalene in terms of ion exchange capacity. At 80 degrees Celsius, the proton conductivity of the naphthalene sulfonate variant reaches an impressive 1.71 Siemens per centimeter. That is more than triple the 0.56 Siemens per centimeter baseline of commercial naphthalene 212. While early life cycle assessments indicate that the energy-intensive manufacturing of graphene currently presents an environmental hotspot, scaling up production is expected to drastically reduce these impacts, offering a highly sustainable and high-performance membrane for future electrolyzers. Perhaps the most radical departure from traditional polymer membranes altogether is the development of solid-state proton-conducting inorganic oxide membranes. Using advanced semiconductor manufacturing techniques like atomic layer deposition, researchers are engineering ultra-thin silicon dioxide membranes. We are talking about structures built one atomic layer at a time. In recent proof-of-principle demonstrations, a chip-scale water electrolyzer based on a 100 nanometer thick phosphorus-doped silicon dioxide membrane achieved a current density of 2 amps per square centimeter at a potential of 2.5 volts. Because these membranes are entirely inorganic, they represent the absolute elimination of PFAS. If successfully scaled from microchip dimensions to industrial multi-cell stacks, these oxide membranes could entirely redefine the thermal and chemical boundaries of low-temperature water electrolysis. But solving the membrane issue is only half the battle. We now have to talk about the catalytic bottleneck, which presents an even more rigid and terrifying barrier to global scale. This is the crisis of iridium scarcity. In a PEM electrolyzer, the oxygen evolution reaction, or OER, occurs at the anode. This reaction is kinetically sluggish. It requires a highly active, incredibly robust catalyst to operate efficiently. But in the harsh, highly acidic, high-voltage conditions of a PEM cell, almost all metals instantly dissolve or corrode into nothing. Historically, iridium, and specifically its oxidized form, iridium dioxide, is the only element that has demonstrated the necessary electrocatalytic activity and stability to survive. The problem is that iridium is quite literally one of the rarest elements on planet Earth. It is found in the Earth's crust at an abundance of only about 0.001 parts per million. To put that in perspective, it is roughly 40 times rarer than gold. Furthermore, there are no direct iridium mines anywhere in the world. It is almost exclusively extracted as a minor byproduct of platinum and palladium mining, primarily in southern Africa. Because of this, global annual production hovers at a minuscule 8 to 9 tons. Currently, conventional PEM electrolyzers require massive catalyst loadings, typically between 2 and 4 milligrams of iridium per square centimeter, just to ensure efficient electron, proton, and mass transport. On a macro scale, this translates to roughly 300 to 400 kilograms of iridium required for every single gigawatt of hydrogen production capacity. If you do the math, it reveals a completely devastating reality. Even if the entire global supply of iridium were diverted exclusively to green hydrogen production, it could only support the manufacturing of roughly 30 gigawatts of capacity per year. To meet global decarbonization targets and replace fossil fuels, the world will need hundreds, if not thousands, of gigawatts of capacity. The United States Department of Energy's Hydrogen Shot initiative, which aims to reduce the cost of green hydrogen to just $1 per kilogram, explicitly recognizes that current iridium loadings make large-scale deployment economically and physically impossible. So how do we bridge the gap between global energy demands and geological reality? Scientists and engineers are employing aggressive structure engineering, oxidation state modulation, and advanced deposition techniques to drastically slash the amount of iridium required per cell. The Department of Energy has set an aggressive target to reduce iridium loading to at least 0.125 milligrams per square centimeter. And recent breakthroughs indicate that the industry is not only meeting this target, but completely surpassing it. Traditionally, electrolyzers utilize catalyst-coated membranes, where a thick slurry of catalyst is painted directly onto the Anion membrane. This method results in terrible catalyst utilization, often dropping below 20%. Much of the precious metal just gets buried deep within the layer, completely isolated from the electrochemical reaction pathways, meaning it sits there doing absolutely nothing. The industry is now pivoting rapidly toward porous transport electrodes and advanced nanotechnology coating. Companies like VS Particle are utilizing single-step dry coating technology to create highly uniform nanoporous layers that slash iridium requirements by a factor of 4. By applying ultra-thin catalyst layers directly onto porous transport layers, the efficiency of the three-phase boundary, which is the exact microscopic point where gas, liquid, and solid meet, is absolutely maximized. This ensures that almost every single atom of iridium is actively participating in splitting water. In early 2025, the Swedish nanotechnology firm Smoltek achieved a massive milestone by successfully demonstrating a hydrogen-producing cell with a catalyst loading of just 0.1 milligrams of iridium per square centimeter. Over a 250-hour continuous durability test operating at high current densities of 2 amps per square centimeter, Smoltek's advanced nanostructure showed absolutely zero degradation. By fundamentally re-engineering the nanostructure to survive the harsh electrochemical environment, they achieved a staggering 95% reduction in iridium usage compared to conventional technology without compromising cell performance. This conclusively proves that ultra-low iridium PEM electrolysis is commercially viable right now. Beyond physical restructuring, chemists are actively tuning the electronic properties of the iridium atoms themselves to make them work harder and faster. Doping iridium oxides with transition metals such as niobium and titanium modulates the electronic structure of the catalyst. This doping effectively stabilizes the intermediate oxidation states of iridium during the oxygen evolution process, resulting in remarkable improvements in both intrinsic activity and long-term durability. Furthermore, by anchoring these doped iridium nanoparticles onto highly conductive, corrosion-resistant support materials, the tiny catalyst particles are prevented from clumping together or agglomerating over time. Advanced architectures, such as ruthenium iridium tantalum oxide nanosheets, have recently demonstrated the ability to operate stably for over 500 hours at 1 amp per square centimeter, with a practically negligible degradation rate of just 27 microvolts per hour. While reducing iridium loading to 0.1 milligrams represents a massive triumph of modern engineering, the ultimate holy grail of green hydrogen production is eliminating the need for platinum group metals entirely. This incredibly ambitious goal is being aggressively pursued through two distinct scientific pathways. The first is the discovery of novel acid-stable, non-noble catalysts for PEM systems. The second is a fundamental architectural shift to an entirely different technology called Anion Exchange Membrane, or AEM, electrolysis. Let us look at the first pathway. For decades, finding a cheap, abundant material that could survive the highly corrosive acidic anode environment of a PEM cell seemed physically impossible. However, researchers have recently identified incredibly promising eco-friendly methods to generate hydrogen without rare elements. A landmark development involves an anode catalyst made from cobalt tungsten oxide. Through a brilliant and novel delamination process, scientists were able to substitute a portion of the tungsten oxide in the crystalline lattice structure with actual water molecules. This substitution resulted in a highly robust catalyst designed to actively involve water and its molecular fragments in its own structural stabilization. During rigorous testing, this cobalt tungsten oxide catalyst demonstrated unprecedented stability for over 600 hours at a high energy density of 1 amp per square centimeter. This record-breaking stability for an iridium-free catalyst in an acidic PEM environment represents a pivotal leap forward in materials science. It heavily suggests that highly scalable, fully non-noble PEM electrolysis may soon become a widespread reality. But while researchers labor intensely to make non-noble metals survive in harsh acidic environments, a rapidly maturing alternative bypasses the acid problem entirely. This is the rise of Anion Exchange Membrane, or AEM electrolysis. AEM technology essentially combines the best of both worlds. It utilizes an alkaline operating environment, highly similar to traditional, old-school alkaline electrolyzers. Because the environment is alkaline rather than acidic, it allows engineers to use cheap, incredibly earth-abundant transition metal catalysts like iron, nickel, and cobalt. But unlike those old liquid alkaline systems, AEM employs a solid polymer membrane. This permits the rapid response times, the high pressure output, and the highly compact design characteristic of modern PEM systems. Crucially, AEM electrolyzers do not use Nafion. This inherently makes them a completely PFAS-free technology right out of the box. And because they operate with base metals, they operate completely without a single atom of iridium. Commercialization of AEM technology is currently accelerating at breakneck speeds. Companies like Dioxide Materials are pioneering the production of large-scale PFAS-free anion exchange membranes, such as their Sustanion line, tailored specifically for high-efficiency hydrogen generation. Meanwhile, hardware manufacturers like Anapter have already commercialized fully iridium-free AEM stacks. Their highly modular systems range from compact 2.4 kilowatt single-core units all the way up to the massive 1 megawatt system known as the AEM Nexus. This megawatt-scale giant combines up to 420 individual stacks to produce a staggering 450 kilograms of highly pure hydrogen every 24 hours. Because these systems are completely untethered from the wildly volatile pricing and the strict supply chain constraints of rare earth metals, AEM electrolyzers possess the true potential to drastically decrease the levelized cost of hydrogen. In fact, recent techno-economic studies are projecting costs rapidly falling to just €1.29 per kilogram, very closely tracking the Department of Energy's most ambitious cost targets. Of course, the sheer magnitude of the technical challenges surrounding PFAS elimination and iridium reduction has spurred unprecedented international collaboration. Fragmented, isolated lab research is no longer sufficient to save the planet. Instead, massive, multinational consortia are aggressively pooling their resources, their data, and their manufacturing capabilities to push next-generation systems out of the laboratory and directly onto the energy grid. One shining example is the SUPREME project. Funded under the European Union Clean Energy Transition Partnership, the SUPREME initiative is a flagship 3-year project entirely dedicated to reinventing green hydrogen from the ground up. Steered by the University of Southern Denmark alongside powerhouses like Graz University of Technology, Turkey's Scientific and Technological Research Council, Fraunhofer, and Ames Goldsmith, the core mission is clear: to industrialize PEM electrolysis systems that are 100% free of fluorinated polymers and operate on drastically reduced quantities of critical raw materials. By vertically integrating their innovations, they are achieving what no single company could do alone. You have the Turkish Council developing the underlying PFAS-free microporous membranes. You have the University of Southern Denmark engineering the ultra-low iridium and highly recyclable catalysts. And you have Fraunhofer producing the finalized electrolyzer materials. Together, this project is completely de-risking the future supply chain and ensuring these novel components can actually endure the brutal realities of 24/7 industrial application. Running parallel to this is the HY-Scale initiative. This is an industry-driven, highly interdisciplinary EU-funded mission focused specifically on upscaling AEM technology. HY-Scale's primary objective is to leap from those modular small-scale units straight to the construction of the very first single-stack 100 kilowatt AEM electrolyzer prototype that fully implements critical raw material-free and PFAS-free components precisely at the cell level. By focusing intensely on cost-effective mass production designs and highly efficient balance of plant integrations, HY-Scale aims to validate this technology in industrially relevant environments, officially reaching technology readiness level 5. This will prove to the world that AEM technology can be confidently scaled to multi-gigawatt levels across Europe before the year 2030. Furthermore, in the Netherlands, the collaborative Voltachem program, co-initiated by the independent research organization TNO, is heavily focused on testing and validating commercially supplied fluorine-free membranes at its state-of-the-art Faraday lab. Recognizing that the European Union's impending PFAS restrictions threaten to completely and temporarily halt all electrolyzer deployments if alternatives are not ready right now, TNO is providing vital, totally independent benchmarking of these next-generation membranes. Their ongoing, highly rigorous testing has shown incredibly promising results, ultimately providing the global electrochemical industry with the rock-solid data confidence required to pivot safely away from legacy Nafion-based standards. Ultimately, the future of the hydrogen economy rests on these incredible scientific achievements. The next generation of water electrolysis is arriving exactly when the world needs it most. The initial wave of green hydrogen technology proved to the world that deep industrial decarbonization was technically possible, but it relied on a fundamentally unsustainable material foundation. The heavy, lingering dependence on toxic forever chemicals and the mathematically impossible reliance on an element as rare as iridium truly threatened to throttle the green energy transition before it could truly begin. However, the rapid, beautiful convergence of nanomaterial engineering, advanced polymer chemistry, and global institutional support is actively and aggressively dismantling these bottlenecks right before our eyes. Whether it is through Swedish nanotechnology breakthroughs utilizing mere fractions of a milligram of iridium, the brilliant invention of cobalt-tungsten oxide catalysts that eliminate noble metals entirely, or the explosive global scaling of PFAS-Free Anion Exchange Membrane architectures capable of megawatt-scale production, the technological leap occurring right now across the globe is absolutely staggering. As we look toward 2030 and far beyond, the fundamental architecture of green hydrogen will be completely redefined. The giant electrolyzers that will power the massive maritime shipping fleets, the high-heat steel mills, and the clean electrical grids of the future will not be constrained by the dark legacy of toxic fluorine compounds or the geological scarcity of precious metals. By engineering innovative, PFAS-free, and low-iridium systems today, the global scientific community is not just making hydrogen cleaner, they are making the scalable, sustainable, and highly affordable energy transition a concrete, physical reality. Thank you for tuning in to Fun Facts Online, where we bring you the cutting edge of science and technology. Stay curious, and we will see you in the next deep dive.